The idea that we can use series to attack functions with singularities is really powerful. So let's take a look at this function, which is pretty straightforward, and we'll see if we can analyze it and figure out what its Frobenius series solutions must be. The first thing that I'm going to note is that this is not quite in standard form yet. This is excellent for computation because there's no fractions, but I can't actually figure out what R1 and R2 are in this form. So step 1 said that I was supposed to put it in standard form and figure out what P naught and Q naught were. So let's write that down. X squared y prime prime plus 3/4 x y prime plus 1/4 xy is equal to 0. P of x is equal to 3/4. Q of x is 1/4 x. You can read those off of the general form of the equation, which is x squared y prime prime plus x p of x plus q of xy is 0. And then that means that p of 0 is 3/4, and that's your p naught value, and q of 0 is 0, and that's your q naught value. Step 2 said we were supposed to find R1 and R2 by using the indicial equation. Step 2 says that we're going to solve R times R minus 1 plus 3/4 R plus 0 is equal to 0. What you're going to find when you do that is that you're going to get the values R is equal to 0 and R is equal to 1/4. And because we're arranging these things so that R1 is bigger than R2, I'm going to call this R1 and I'm going to call this R2. The next thing I want to note here is these don't differ by an integer, which means that we know we're going to be able to find two linearly independent Frobenius series solutions to this. What did step 3 say? Step 3 said that we're allowed to assume that it has a Frobenius series solution. That means that we're going to write down that we believe that y is equal to x to the r sum from n equals 0 to infinity of a n x to the n. Now I don't want to go putting in the r's at this point because I'm going to have to come up with the same recursion for this equation for two different series. The only difference is going to be the r that I plug in. So I'm going to save plugging the r in until I've actually computed what the recursion must be without the r plugged in. Unless you just like doing a lot of fraction math and the same thing over and over again. I suggest that this is the way that you do it. To do that, we're going to need expressions for the derivatives. And so we're going to combine this together and write this as the sum from n equals 0 to infinity of a n x to the n plus r. And then the derivative expressions turn out to be pretty easy. Y prime and y double prime. Now these series all still start at 0 because unlike the power series case, the constant term and the x to the first term don't even exist. And if they do, they don't disappear in the same way because this x to the r is being multiplied through. So you can't assume that you have an x to the 0 and x to the 1, that when you take the derivative, they just vanish. Now that I've got a form for the derivatives, I'm going to plug those in to the equation to derive the recursive relation. The particular equation that we were working with is, and rewritten with the Frobenius series plugged in, I get the following. Okay, so this looks like an algebraic monstrosity, but it's not so bad because we're going to use the same exact strategies we used to find the recursion in the power series things. First, we're going to multiply everything in, then we're going to make the powers match, then we're going to make the indices match, then we're going to squish it all together to get a recursion. So the way that we're going to start is we're just going to multiply all the coefficients in and see what comes out. So for the first sum, what happens? The 4x squared goes inside and we get a 4 right here. And then the squared of the x goes in and hits the -2 right here and adds 2 to it, and so that disappears. What happens to the 3x? The 3 goes inside, and the x goes in and adds 1 to this power, but n plus r minus 1 plus 1 is just n plus r. And finally, the x that's out here goes in and adds 1 to this power. We don't have powers that match. And so we're going to have to shift something in order to make that happen. And so what we'll do is we can actually replace n plus r plus 1. We can subtract 1 from all of the iterations of n. And that means that we have to add 1 to the starting place for this particular series. So what do I mean by that? I can replace this with the sum from n equals 1 to infinity of a n minus 1 x to the n plus r. That these series are the same. And you know that they're the same because if you put a 1 in here, you get a naught 1 plus r. If you put a 0 in here, you get a naught 1 plus r. So these two series are the different representations of the same sequence of terms. So now we've got three sums, but now they don't all start at the same spot. The powers match, but the starting indices don't, because we have 0 and 0 and 1. So what we should do is we should pull off the n equals 0 terms of the first two sums. So what do those look like? If you put n equals 0 into the first sum, you would get r, well, there's a 4, and then an r, and then an r minus 1. So by pulling this out, now I start this series at 1 instead. Same thing here. I'm going to pull out the term corresponding to n equals 0, which means if you put in n equals 0, you would get 3 times r times a0. But then I've pulled out the n equals 0 term, so I have to get rid of it and start this series at 1. Now, one thing to notice is that these two terms are actually where the indicial equation comes from, right? Because if you take these two things and you combine them because they're both the coefficients of the a naught term, and you set it equal to 0, you just get this equation back again. So this equation right here comes from the combination of these two equations right here being equal to 0. And we already know the answers to this. R1 and R2 are 1/4 and 0. So what we're going to do to get the recursion is we're going to smash all the rest of these together. That'll give us the following. So when I take those series and put them together, this is the result. I could do this because the powers match and the indices match. So when I've taken the series and put them all together, because the powers match and the indices match, this is the result. And this just looks like a recursion like we would have gotten in the previous section about series solutions. I can take this thing now, since it's equal to 0, I can assume that all the terms must be equal to 0. And that means I get the expression 4n plus r, n plus r minus 1, plus 3n plus r, an plus an minus 1 is 0. And that holds for n is equal to 1, 2, 3, and so on. And that's going to give me a recursion. In fact, I can make it look nicer by dividing through by all of the factors over here, and I'll get an is equal to 1 over 4 times n plus r times n plus r minus 1 plus 3 over n plus r. And this I can use to generate terms. There's only a gap of 1 here, and that means that a naught is going to determine every term in the series. We have our recursion relation. We know the r values that we need to plug in to find the Frobenius series. So let's just start, since we know that we've got two and they're distinct and they're both going to exist. I've got two distinct values of r. I can start whichever one I want. I'm going to start with r equals 0. So without any r values plugged in, this was our recursion. When you put in r equals 0 and you do the algebra, simplify, this is what falls out. But now we're just in the land of regular old series solutions. So I can figure out the coefficients in terms of a naught just by plugging in values of n. So for n equals 1, we get the equation a1 is equal to n equals 2, n equals 3. So I've got a pretty clear idea of what the pattern is here. You can see that what's happening is I'm getting this factorial-like structure coming out on the left. And over here was a 3, 7 times 3, 11 times 7 times 3. So I'm just multiplying down, starting at the top and going to the bottom. If I wanted to, I could use that to figure out how to write a pattern in terms of n and r, but I don't need to do that. I can just write down an expanded series if I feel like, without putting in sigma notation, to say the following. I know that my solution then is y is equal to x to the r times the sum of an x to the n. Well, r was 0, x to the 0 is 1, and that means that the series solution for this just looks like a naught times 1 plus 1/3 x plus 1 over 2 factorial times 7 times 3x squared plus 1 over 3 factorial times 11 times 7 times 3 x to the third, and so on. So there's my first series solution. Remember that this corresponds to the power of x to the first, x to the second, x to the third, and so on. So that's just a power series solution. Well, what happens for the other value of r? Well, for the other value of r, when you plug r is equal to 1/4 into the recursion, it collapses into an is equal to 1 over n times 4n plus 1, an minus 1. And now we just do it the same way again. Remember, we're making the assumption here that our solutions look like y is equal to x to the r, the sum of an x to the n, and we're looking for some expression of the an's in terms of a naught. N is equal to 1 gets me the equation. N is equal to 2 gets me the following expression for a2. N equal to 3 gets me the equation. So it's clear what the pattern is doing, And once I've got the pattern, I can write down an expanded series solution of the following form. Y is equal to x to the 1/4, because that's the x to the r term in the Frobenius series, times 1 plus 1 over 1 times 5x plus 1 over 2 factorial times 5 times 9 x squared plus 1 over 3 factorial 5 times 9 times 13 x to the third, and so on. So that's it. We found our two linearly independent Frobenius series solutions to the equation. It's a lot of elbow grease, but the math isn't hard. It's just knowing how to work with these series. And the steps that we did are important in the way that we did them. So you'll note, what we did to solve this was, we assumed that we had a Frobenius series solution. We put it in standard form, and we figured out what P naught and Q naught had to be. We solved the indicial equation for R1 and R2. We built the recursion generically in terms of R. Then we plugged in our specific R's and used recursion to figure out what the series solutions needed to be. So the behavior of a Frobenius series, in some sense, is determined by what the values of R happen to be that you attach. So the growth or shrinking of the way that a Frobenius series behaves as you come into a singularity is determined by what the R values happen to be. Because that x to the r term in the front is going to dictate something about how quickly or how slowly your function is approaching infinity or some constant as you get closer and closer and closer to some singular point in the differential equation. That can be interpreted in various contexts, but what we're trying to do right now is build an idea of how to even find a solution when the equation doesn't even appear to be defined at a particular point. All right, practice these. I will post more examples in the OneNote notebook, and good luck.